Hey everyone, and welcome to This Explainer. Today we're diving deep into the absolutely fascinating world of chemical reactions. We're going to put on our detective hats and take on the role of, well, chemical detectives. You know, every single day, trillions of chemical reactions are happening all around us, and even inside of us, usually completely invisible. It's the foundation of materials science, forensics, biology, literally the entire universe. So our job today is to learn exactly how to spot the hidden physical clues that prove a fundamental molecular change has actually occurred. And, just as importantly, we're going to learn how to decode the universal scientific language used to officially record those complex changes, chemical equations.
So right off the bat, how do you know a new substance is actually formed? Think about everyday changes you see around your house or your neighborhood. If you leave a bicycle out in the rain, rust eventually coats the metal, right? If you watch a piece of wood burn in a campfire, it completely turns to smoke and ash. Or maybe you've accidentally left milk out on the counter and watched it curdle. Gross, but it happens. How do we prove a chemical change happened in these scenarios? Well, we have to contrast this with a physical change. Like if ice melts into water, its physical state changes, sure, but its fundamental molecular structure, H2O, remains exactly the same. But with a burning log, that wood is actively oxidizing into carbon, ash, and gas. Something entirely new has been created in the universe. And that is the exact mystery we are solving today.
Okay, let's take a quick look at our roadmap. We'll cover 1. The mystery of change. 2. 3 clues of chemistry. 3. Reactants versus products. 4. Writing chemical equations. 5. Solving real chemistry cases. And finally, 6. Stay curious, stay safe. Let's get right into it.
Part 1. The mystery of change.
A chemical reaction is simply a process where starting substances change into completely new substances. But why do those properties change so drastically? Well, it all comes down to the microscopic level. Down there, the actual chemical bonds between atoms are being aggressively broken and reformed. The new substance ends up with an entirely new molecular structure. That's exactly why a highly flammable gas like hydrogen and a combustion-fueling gas like oxygen can combine to form water, a liquid that literally puts out fires. Wild, right? Now, it's also absolutely crucial to remember the law of conservation of mass here. We aren't magically making new matter out of thin air. No way. We are simply rearranging the existing atoms into new configurations. The pieces of the puzzle stay exactly the same, but the final picture they create is completely transformed.
Moving on to Part 2. 3 clues of chemistry.
The cool thing is, nature actually gives us very specific physical hints when these new substances form. It's like a trail of breadcrumbs. Whenever you're investigating a potential reaction, you want to look for 3 primary indicators: a color change, the formation of a precipitate, and the release of a gas. Let's take a color change, for example. Did you know the Statue of Liberty wasn't originally green? It was a shiny copper. That massive color shift is the result of a chemical reaction called the oxidation of copper over decades of exposure to the elements. Another major indicator is the sudden release of a gas. If you mix 2 non-gaseous things together and suddenly see rapid bubbling or fizzing, well, that bubbling means a gaseous compound that literally didn't exist a second ago has just been born and is now rapidly escaping the solution.
Now, you might be wondering about that middle one. A precipitate is a cloudy or solid formation that appears when liquid solutions are mixed. To understand why this unexpected solid forms, seemingly out of absolutely nowhere, we have to talk about solubility. When 2 clear liquid solutions react, they're busy breaking and forming new bonds. Sometimes the brand new molecular compound they create happens to be completely insoluble in water. Because it just cannot dissolve in the surrounding liquid, it immediately crashes out of the solution. It forms a suspended solid powder or a cloudy mass that eventually just sinks right to the bottom. It's a massive, glaring, visual clue that atoms have rearranged themselves into a new, insoluble structure right before your very eyes.
All right, Part 3. Reactants versus products. Reactants are the starting substances, and products are the new substances formed. This is the universal way chemists organize the timeline of a reaction. Reactants always come first. They're your chemical inputs. Products are the entirely new chemical outputs. Think about how this differs from just, say, mixing ingredients in a bowl. If you bake a batch of chocolate chip cookies, you can theoretically still identify the chocolate chips, right? They haven't fundamentally changed their chemical identity. But in chemistry, the reactants are fundamentally consumed and destroyed in order to birth the products.
The starting materials literally sacrifice their original molecular structures so that the final products can exist. It's a total one-way street.
Part 4. Writing chemical equations.
So, once we know our inputs and outputs, how do we write it down? A word equation simply writes out the names of the substances, like hydrogen plus oxygen yields water. Notice that arrow in the middle? In chemistry, that arrow means yields, or turns into. It's essentially the equal sign of chemistry, but honestly, it's much more dynamic than a math symbol. It specifically denotes that one-way street of chemical transformation we just talked about. We read this as the reactants, hydrogen and oxygen, react to yield the product water. It's an incredibly clean, universally understood notation. It summarizes exactly what happened during the molecular rearrangement without getting bogged down in paragraphs of descriptive text.
But we can do even better. A formula equation replaces those words with chemical symbols, like H2 plus O2 yields H2O. Instead of relying on English words, which, might not translate globally, we use the standardized symbols from the periodic table. But to truly speak the language of science, we have to go back to that law of conservation of mass we mentioned earlier. Matter cannot be created or destroyed. Because of that, a chemical equation isn't truly finished until it is perfectly balanced. The exact number of atoms that go in as reactants absolutely must come out as products. To make H2O, you actually need 2 hydrogen molecules for every 1 oxygen molecule. So a fully balanced equation is written as 2H2 plus O2 yields 2H2O. This step up from a basic word equation creates a perfectly precise, mathematically sound sentence of science.
Let's apply this to a real-world example. Vinegar plus baking soda yields carbon dioxide gas plus other products. You've almost certainly seen this classic reaction in a school volcano project, right? But let's elevate it using precise chemical terms. You are actually mixing acetic acid, which is the vinegar, and sodium bicarbonate, which is the baking soda. When these specific reactants collide, they undergo a rapid transformation that yields several things, but most notably, carbon dioxide gas. The telltale release of those violent gas bubbles proves definitively that our products have successfully formed. And here's the key. That gas was not just trapped inside the baking soda waiting to get out. No, it was synthesized in real time by the breaking and forming of new molecular bonds.
Moving on to Part 5, Solving Real Chemistry Cases. A reaction signs observation table is a fantastic tool because it perfectly maps our everyday examples to their starting reactants, final products, and specific physical clues. Take the rusting nail. The reactants are the iron in the nail and the oxygen in the air. The new product is iron oxide, commonly known to us as rust. And the indicator we observe? A distinct color change from silver to reddish-brown. Or consider browning fruit. You bite into an apple and leave it on the counter. The fruit undergoes a process called enzymatic browning, where it reacts with oxygen. The product is the newly oxidized browned fruit tissue, and again, our visual clue is a stark color change. Mapping out the inputs, the outputs, and the visual evidence is exactly how you bring order to the chaos of chemical transformations.
And finally, Part 6. Stay curious, stay safe.
Do not mix household chemicals without adult or teacher supervision. Listen, while analyzing reactants is deeply fascinating, understanding the power of reactants in products isn't just an academic exercise. It is absolutely vital for your safety. Many common household cleaners are highly reactive. For instance, if you were to mix bleach and ammonia, 2 incredibly common cleaning agents, the resulting chemical reaction synthesizes deadly chloramine gas. Being a sharp chemical detective means respecting the profound power of molecular transformation. It means being safe, being methodical, and always relying on proper guidance rather than blind experimentation. So, what safe, everyday chemical reactions will you observe next? Now that you know how to spot the physical clues, the colors, the gases, the precipitates, and how to decode the chemical equations that govern them, consider this. Every breath you take, every thought firing in your brain, and every single star burning in the night sky is just a relentless series of reactants turning into products. You, my friend, are a walking, talking chemical equation. So keep your eyes open for the evidence happening right in front of you. Thanks so much for joining me on this explainer, and stay curious.